Find the minimum value of b1, which will minimize the value of z. In this problem, the value of z decreases as b1 increases until a certain value of b1, which we'll call b1 star. Calculating the objective function value as the quantities on the right-hand side of the constraints vary is a sensitivity analysis technique used in many linear programming applications called right-hand side ranging. To begin this problem, we'll put the constraints into standard form of ax equals b. To do so, we'll add slack variables x3 and x4 to the left-hand side of the first and second constraints, respectively. Since all x variables are non-negative, the first constraint indicates the minimum value of b1 is 0. Next, we'll set up the network tableau shown here in its entirety, with the two slack variables x3 and x4 as the basic variables, equal to the rightmost column, column B. From here, our strategy will be to select a value of b1, solve the problem for x to identify the optimal basis b and its inverse, b inverse. Step 3 is to calculate the range of b1 values for which the basis b is feasible. And the fourth step is to define the objective function value, z, for that specific range of b1. Then we'll repeat the process. In the subsequent iteration, we'll select a value of b1 just beyond the range defined in step 3 from the previous iteration. We'll continue this loop until the entire feasible range of b1 values are exhausted and the plot of z is completed. Then we can identify the minimum value of b1 which minimizes z, b star. From the first constraint, we identified the minimum value of b1 is 0. Then for step 1, we'll select b1 to be slightly greater than 0, denoted as 0 plus. If we select x1 to enter the basis, it will replace slack variable x3 and an optimal solution is found. This makes variable x1 and x4 basic, and the B matrix equals 1, 0, 2, 1. In linear programming, the constraint set in standard form is ax equal b. Matrix A is composed of constant values which are either associated with basic variables, b, or non-basic variables, n. The decision variables, x, are non-negative for all basic variables xb, and equal 0 for all non-basic variables xn. Since variables xn equal 0, they can be removed from the equality, and we're left with bxb equals b, where the little b on the right-hand side equals the far right column in the tableau. The second step is to identify b and b inverse. We've already identified matrix B from the tableau, and we can calculate B inverse, which is the adjugate of matrix B divided by the determinant of matrix B. The third step is to calculate the range of B1 values, which are feasible for the basis B. To do so, we'll solve for xb, which equals b inverse b. After plugging in matrix B inverse and vector b, and knowing that xb is non-negative, we can calculate the range of b1 as at least 0 and at most 2. Step 4 is to define the function z for this given range of b1 values. The objective function value z equals c transpose x, which can be reduced to c transpose xb. Plugging in the appropriate values, z computes to minus b1. When plotted over the range of 0 to 2 for b1, the value of z slopes down from 0 to negative 2. The next step is to repeat the same procedure using a value of b1 just beyond the previous range of b1. So we'll assign b1 to be slightly greater than 2. Next, to identify b and b inverse, we'll solve the tableau by first pivoting about variable x2, and then pivoting again about variable x1, and a solution is found. Since x1 and x2 are the basic variables, matrix B equals 1, 2, 2, 1, and matrix B inverse equals negative 0.333, 0.667, 0.667, negative 0.333. Next, we'll calculate the range of b1, recalling that vector b equals b1, 4, and setting b inverse b to a non-negative value. We plug in b and b inverse and learn b1 is at least 2 and at most 8. The next step is to define the equation z for this range of b1. As before, z equals c transpose b inverse b. After plugging in the appropriate values, we learn z equals negative 0.333 times b1 minus 1.333 for values of b1 between 2 and 8. If we add this line segment to the plot, we notice the value of z drops to negative 4 at b1 equals 8. Next, we'll set b1 equal to a value slightly greater than 8, denoted as 8 plus. Using the simplex method, variable x2 will enter the basis in place of x4, and after pivoting about variable x2, a unique optimal solution is found. Variables x2 and x3 are basic, and that makes the b vector equal to 2, 1, 1, 0, and matrix B inverse equal to 0, 1, 1, negative 2. This time, the range for b1 is all values at least 8. Solving for z, we learn z equals negative 4. If we add this line segment to the plot, we notice that any additional increase in b1 beyond the value of 8 will not allow for a lower value of z. Therefore, the minimum value of b1, which will minimize the value of z, is b star, which equals 8. When reviewing the possible solutions, the answer is D.